Okay, guys, so this is our homework that was assigned on Wednesday. It's over net force and force diagrams worksheet. This one I asked you guys to do on paper. Some of you guys forgot to do it. That's okay. The best thing you can do now is to follow along and try to just stay with us, okay? Because me explaining this is half the battle. Like, this is half the good thing from this is just getting the understanding from hearing it told to you. The other half is practicing it when I tell you to, but if you pay attention, you're most of the way there. You'll do fine on the tests and the quizzes, okay? I think. So first one starts with an example. It says, Mr. Short lifts a heavy box over his head with one push of his arm and a force of 250 newtons. Gravity is pulling down on the box with a force of 200 newtons. And there's a question here. It asks, what is the net force? Let me notate here. What is the next force acting on the box? What is the net force acting on the box? Okay. So here we've drawn the free body diagram in our example. All right. It shows the force of Mr. Short's arm pushing up 250. Okay. And it shows gravity pulling down 200. When we find the net force, we might say, well, what's net force? We've been calling it the resultant force, but it's the same thing. Okay. I think I did explain that at one point and try to tell you guys. So those of you who were able to get this work done, hopefully you found that the resultant force was 250 minus 200, the resultant being 50 newtons upwards, 50 newtons of upwards force as the resultant force. Any questions on the example? I'll pull the chat up so I can see your questions if you guys have questions as we go here. The next problem says, two stellar science students are pushing a box, one on each side. Kenny is pushing the box with a force of 10 newtons to the left. So my approach to this, I'm going to go ahead and I'm going to start drawing. I'm going to start drawing my force vectors because that just makes things easier for me. As I read them, I'll draw them. You might decide that you like to do it a different way, but this is the way I like it. So Kenny's pushing. If he's pushing the box to the left, that means he's touching it here at this point, and he is pushing it this direction. Okay. And it says 10 newtons. Okay. Now, I can't just say 10 newtons. I need to label this force. I need to give it a name, okay? Because I don't know if this is 10 newtons of friction. I don't know if this is 10 newtons of gravity, 10 newtons of thrust or drag or anything. It's 10 newtons of Kenny. And Kenny would be an external force. He's a push or pull from outside the object, okay? One of the ones we haven't labeled otherwise, like gravity. So it's F1.
I know Kenny, you can't push that hard.
Kenny's name is F1 in this problem. We renamed him. He's F1, force number 1. What am I doing wrong? Now we're talking about Michael. Michael pushes the box with a force of 15 newtons to the right. This arrow vector needs to be 1.5 times as long because it's 1.5 times as much force. But I'm not going to pick about that. As long as it's a little longer, it makes sense. Okay? This is 15 newtons. Okay. But Michael's the second person mentioned in this problem, the second external force we talk about. So we're going to give him the name F2, force number 2. F1 equals 10 newtons, F2 equals 15 newtons. Okay. It says draw a diagram. What is the net force? Well, there are other forces acting on this object, on this display. There are. There's gravity, okay? And there's a normal force. But we don't know what their amounts are. So a lot of times we get away with drawing those. At any rate, we draw that. We don't have amounts in here, we can't, so we won't. What we do know is the box is not falling, the box is not flying up in the air. So that tells us that probably those forces balance out. gravity, whatever this number is, it equals the other. They're equal. They cancel each other out. Okay? Actually, I need to erase a lot of this. It's just not getting in our way. Okay. But we could draw those. If we felt it necessary to label every force, we could draw those. I have a message in the chat here. I got a sniffy nose. Thanks for keeping us in the loop on that, Nevada.
Macy also said that her reading as well.
Yeah, I saw where she said she forgot that. So we're asking what's the net force? What is the resultant force? It's the same thing. It means the same thing. The resultant force is the pulls and the pushes subtracted, which side wins and by how much? Okay? 15 minus 10 gives us 5 newtons. And which side won? Well, Michael pushed harder, so he won. He pushed to the right. So it is 5 newtons right. Does this make sense to everyone? The way we find the resultant force and the way we can find this using our diagram, our free body diagram, how this helps? Is there anyone that has any questions about what we found here?
Nope.
Something in the chat, it says no. Of course it says no. Every time I ask, does anyone have any questions, the only answer I get is no, which I guess is a good thing. I must be explaining it well. Okay, I'm going to clear the drawings. Michaela says, nah. Okay. Here we have another couple of problems. I'll try to work these both in the same without scrolling here. Okay. All right. During the tug of war, Abby thought she was Supergirl and tried to beat Thomas. Abby with one arm, I don't even know how many arms she used. Okay. Abby on the road, other on her side, applied 100 Newton force to the left. Abby does it's a tug of war, so she's pulling, right? So she's going to act on the edge of the road. That's not super duper important in this class, but when we draw our diagrams, we might as well do it accurately. So 100 newtons to the left. F1. Abby is now F1. F1 equals 100 newtons. Thomas applies 100 newtons of force to the right. It tells us he uses both hands. Doesn't matter. F2 equals 100 newtons. Of course, in theory, we've got forces of gravity acting down, normal acting up, right? Fg equals Fn, Fn equals Fg. Right? We know that the rope is not accelerating upward or down, but we can ignore that in the diagram just to keep our page from having too much clutter. Okay. The question is, what is the resultant force? In the chat, tell me what is the resultant force. If Abby pulls 100 and Thomas pulls 100, what's the resultant force? Who wins and by how much? Tell me in the chat, who wins, how much? That says 200. Okay, not a bad guess. Very useful. Chris says 0, question mark. Ryan says 0. Chris says, I don't know. Well, look, if Abby pulls 100, Thomas pulls 100, they pull the same amount in a tug of war, there's not going to be a winner, right? So we do the same thing. Forces that act in opposite directions get subtracted. 100 minus 100 equals 0. Now, if Abby had, let me use a different color. If Abby had pulled this way, and they both pulled, if F1 had pulled this way, then they would add together. But that's not what happened, okay? That's not what happened. What happened was they pulled opposites. Because they're opposites, opposites subtract. Opposites subtract. So 100 minus 100 equals 0 newtons. 0 newtons of force. Okay. Just like when we were doing our vector diagrams with the grids, this is the same thing except for just on paper, and instead of counting grid squares, we are looking at what's labeled here. 100 newtons minus 100 newtons. Okay. I believe that this makes sense more or less for you guys. I really do think that. Abby decided to finally take this seriously. She put both hands on the rope. She applied 150 newtons of force to the left. Oh, I gotta show you some back here. Okay. Thomas still struggled. He was already trying his best, and so he could only apply 100 newtons to the right. Now, Nevada, when forces act in opposite directions, what do we do with them? What do we do with forces that are opposite? Opposite what? You say it out loud, or you can say it in the chat. Forces acting in opposite directions. Let me give you some options. They either add together or they subtract. If they go in opposite directions, what do they do, Nevada? Subtract. Exactly. Exactamundo. So 150 minus 100 gives us 50 newtons. Okay, so we got 50 newtons, but we need to know the direction of the resultant force. The direction goes with the winner. Who won? Abby did with 150 over here. How much did she win by? 50 newtons. 50 newtons left. 50 newtons to the left is the resultant force. So now that we know the resultant force, we could take this information here and we could push this into our F equals ma equation. We could find out how much mass would, or how much you would accelerate, how much mass with that. You could weigh the rope. You could find the mass of the rope. You could find the mass of the rope by measuring how much it accelerated and how much force was applied. And these are physical things we can know about it, just with the data that we can collect. And yeah, we're not doing that. We're not doing it yet anyway. Okay. Cole, Blaine, and Haley. Okay, they're trying to push Haley on a wheeled chair, not a wheelchair, a wheeled chair with enough force that she can run into a fourth person, Mr. Young. They figured out they needed 50 newtons of force to get the chair to hit him. They were both applying force toward Mr. Young. Okay, here we go. Cole was applying a 20 Newton force to the left. So I'm going to go into a diagram and I'm going to draw a 20 Newton force. That, my arrows are not good. I gotta do better arrows. Good enough.
There's an error tool, you know.
I know. So he's doing 20 newtons to the left. Cole, because he's the first person that applied a force, he gets the label F1. Blaine was trying as hard as he could, and he was applying 15 newtons to the left. That's a separate force. I hope that's readable on your screen. F2 equals 15 newtons. Okay. What was the net force if we ignore friction? What's the resultant force of these two guys' push? If the forces act in the same direction, Macy, what do we do? Macy, what do I do if forces act in the same direction? What do I do with these two guys' force? Macy or Ryan, whoever answers it first, you get a high five. These forces act in the same direction. What do I do with them, Ryan? Macy, anybody? Add. They get added together. The forces act in the same direction. Cole and Blaine were both pushing in the same direction. Actually, I guess on your screen, in the same direction on the chair. If Cole pushes 20 and Blaine pushes 20, then their forces get added together. Got you, Chris. So they add together. The net force is 20 plus 15 equals 35 newtons of force. Did the chair hit Mr. Young? It says they needed 50 Newton force to hit Mr. Young. Did they have that? Oh. The next question is, how do they get the chair to hit Mr. Young? How can they do that? They're going to need more force. Okay, they only have 35, but they need 50. Okay, so they need 15 newtons of force to the left is needed. Can we see now how free body diagrams can help us? I mean, they can help us in engineering. If we're trying to build a bridge, we're trying to build a race car, we're trying to figure things out, trying to build a rocket. Free body diagrams help us model all this on a piece of paper so that we can find out how much more force we need on something, or how much less we need on something sometimes, or whatever. Okay. In a fourth period battle, the girls were able to overcome the boys 3 times in a tug of war. The boys had 3 individuals, each pulling with a total force 30 newtons to the left. Okay, this wording is confusing. Okay, I'm going to throw away this word total because that just confuses us. The boys had 3 people pulling 30 newtons to the left, meaning 1, 2, 3. F1 equals 30, F2 equals 30, F3 equals 30. The 5 girls together, I'm going to use a different color just to make this, because I got a lot going on here. The 5 girls together were able to pull the rope toward them, presumably to the right, tug of war, right? F4, because it didn't tell us how much each of those pulled. We can figure that out later, but we don't know that yet. It's 50 newtons. And that area is probably too long. What was the resultant force? Resultant force. 30 and 30 and 30 is 90. The forces are acting in opposite directions, so it's 90 minus 50. Okay, that gives us 40 newtons of force. The boys won by 40 newtons, and they won to the left. And they won the battle to the left. What was the minimum amount of force each of the 5 girls applied? Well, the minimum amount of force each of the 5 girls applied was 0. Okay? So this question is dumb. It's not very well written. I didn't write this thing. I think they mean the average. The average amount of force that each girl applied. If you have 5 people and together they do 50 newtons of force, and the answer is 10. And I'm not getting into that. I'm not going to read any questions, because I don't like the way it's written. All right. What time is it? Yeah, it's about 10:30. I'm going to wrap this up. I'm going to do one more problem, and we are going to quiz over this information Monday. So make sure you've got this paper finished. Make sure you're using my examples to do your example. Okay. During the second period, Alex was a beast. She resisted the forces applied by 5 people in her class at once. They applied a total force 95 newtons to the right. 95 to the right. And Alex still did not move. Okay. Alex was sitting still. They applied 95 newtons to the right, but she didn't move. If she did not accelerate to the right, the question, what we're asking is, what was the net force? How much is this force if there was no change in her motion? We know that she balanced their motion. So what was her force? The other way. Well, if there's no change in motion, if A equals 0, A equals, that's not an A. I'm showing you math on this, but you don't really need math to describe this. You can figure this out without math. A equals 0, A equals F over M, and A equals F over, let's say, a mass of 1, right? 0 equals force over a mass of 1. How much force? I'm just confusing you. They pull 95. She has to pull enough that she won't move. Well, she has to pull 95. That's 2 equals 95. If she doesn't change her motion, if she doesn't move, then she must have pulled the same amount the opposite way. Okay, we know this because to not move, not change your motion, for being more specific, the net force has to be 0. In other words, how much force was Brianna? I think they mean Alex. Whoever wrote this sheet got a little inconsistent. How much force was Alex pushing back? 95 newtons left. This is this right here. The big story here with this, guys, the thing that we need to make sure we know how to do is we need to know how to draw a free body diagram. If I tell you what the forces are, I tell you 95 to the right, you need to be able to go that's the hard part. Okay? If I tell you there's a book on a table and gravity and normal force both act on it, you need to be able to draw a box and say FG, FN. Okay? If I tell you that I didn't push that box, I then push that box to the right with 10 newtons of force, well, then you need to be able to just go F1 equals 10 newtons. If I then go on to say, yeah, but friction acted on the box, and it slowed the box down, or it made, I say friction acted on the box with a force of 2 newtons, you just need to go F equals 2 newtons. You draw the free body diagram. From there, you need to be able to say, okay, well, what was the resultant force? Well, Fn and Fg cancel out, so the up-down resultant is 0, right? To the right, I go 10, the left friction takes away 2, our resultant force is going to be 8 newtons. That's basically the quiz. The quiz is going to be asking you to more or less to draw this, to create this. Okay? I think you guys will nail it. It's really not complicated, all right? It's really not that bad. You guys got it. You guys have any questions about this or need me to go over any more of this? I'm going to post this lecture that I just gave here on YouTube, and I'll be available on the Zoom call for the next 15, 20 minutes. Thanks. I am going to post the link in the chat to my calendar that shows what's coming up.